So we're going to talk about what happens when an acid combines with a base. So when this happens, the hydrogen ion from the acid and the hydroxide ion from the base will combine to form water. So this is water that's formed is completely neutral. So this type of reaction is referred to as a neutralization. You might be thinking that this looks like a double replacement reaction. Well, neutralization is a special type of a double replacement reaction. So you'll always have an acid plus a base, or a base plus an acid, to make water and then a salt. So salt, remember, is a generic term to describe ionic substances. So sodium bromide here is an example of a salt. Also, pretty much whatever's left over when your acid and base react are going to be your salts. So let's take a look, kind of reviewing Unit 5 a bit. We have sodium hydroxide, which is NaOH, reacts with hydrochloric acid, which is HCl. So again, we're going to be predicting products. So it's a double replacement reaction. Our substances are switching places. So we're going to make water, which is coming from the H from the HCl and the OH from the sodium hydroxide. And in this case, we're going to also have sodium chloride. This reaction is balanced. And one of the things that might be asked of you is identify the salt and water. Water is super easy to identify. The salt is kind of whatever is left over. You have your base and your acid as well. You could also be asked to identify those as well. So you have phosphoric acid, which is H3PO4, reacting with calcium hydroxide. This one's going to be a little trickier because your phosphate and your calcium have different charges. So what you're going to end up doing, again, you're switching the partners. So you're going to have Ca3PO4 parentheses 2. So calcium has a +2 charge, phosphate has a -3 charge, so you have to balance the charges in your chemical substance. And then you'll still have water as a product. You're not going to make like hydronium here. It's always going to be water as one of the products. We can then balance the quantities by balancing the reaction. So for this one, we will need a 3 in front of the calcium hydroxide, a 2 in front of the phosphoric acid, and then that will end up with 6 waters. So I always like to take a look at the salt, decide to help me balance everything. You can still do it the way that we've been doing, where you write down your substances and your polyatomic ions to balance your reaction. The acidity of a chemical compound is determined by the location on the pH scale. This scale, acids have a pH of 0 to 7, bases are 7 to 14, and neutral compounds have a pH of exactly 7. So you'll notice here I put several zeros to represent exactly 7. So technically, if you have a pH of 7.01 or 6.999, those are technically not neutral. So in order for it to be neutral, it has to be exactly 7. So you probably have heard of pH in biology. This is used to denote the hydrogen ion concentration of a solution, but there's also something called the pOH, and this is used to denote the hydroxide ion concentration of a solution. So P represents the power, so you can kind of think of it as the power of hydrogen and the power of hydroxide. And when we look at the relationship here in a few moments, we'll see why that makes sense. So taking a look at this table, right off the bat, there's a few things that I want to point out. If you have pH, you have pOH. Notice when you add the pH plus the pOH together, it equals 14. That is not a coincidence. The pH and the pOH are related to each other, and this is the relationship. When you add them together, it's going to add up to 14. So I'm going to start writing in some of the values for our hydrogen ion concentration so that we can note the relationship. So the pH value becomes the negative exponent for the hydrogen ion concentration. So if you think of what the negative exponent means, it means your number is getting smaller and smaller. So as your pH is increasing, your concentration of hydrogen is decreasing. So we can write in the rest. The same thing happens with pOH and hydroxide concentration. The difference is you're starting at negative 13, you're going towards 1 when you get to a pOH of 1. So this again shows their relationship, and we're going to talk about a few ways that we can use these values to help us calculate. So we're going to practice finding the pH using the equation here. So you're aware, logarithms actually have their own unique set of rules for significant figures. However, we're not going to use them. We're going to just kind of replicate the quantity of sig figs that are there. Usually in problems on a quiz or a test, it will say give so many sig figs in your answer when you're doing these calculations. So on your calculator, we're going to be using this log button, which is right next to the 7. And we're also going to be using the 10x that's right above it. So second log would be 10x. So when you push the log button on your calculator, it'll bring up the word log. If you push second log, it'll bring up 10 with either a little caret or an exponent, depending upon the type of calculator you have. So let's practice this with the first one. So our equation is right up at the top. We're going to do negative log of the hydrogen concentration in order to determine the pH. So we're going to type in negative log of 0.045. We're going to hit enter, and this gives us our pH value. So it has lots of sig figs. We have 2 sig figs in our number. We're just going to keep 2 sig figs. So my pH is going to be 1.3. So what I would like you to do is I would like you to try the remaining ones. So these are the values you should have gotten. A few things to point out here. Notice how I wrote no units with my pH value. pH has no units. So if you write a unit when you aren't supposed to have one, that's still the wrong unit. So we don't want to write out units. So notice the other thing. So the ones that are written in scientific notation, the number that is the exponent is very close to the number that you end up with. That's a good way to check. Another thing, the ones that are not, if you put them in scientific notation, it gives you approximately the value for the pH. You're always going to have access to a calculator that has the log function. You'll always be able to use that for you. Just something to kind of keep in mind here. Some helpful hints. We're going to be doing the opposite thing. In the next example problems, we're going to be finding the hydrogen concentration based off of the pHs. So the first one we have is 5. So if we go to our calculator, what we're going to do, we're going to hit the second log and then negative pH. So the first one was 5. Yep, 5. And then hit enter. Now, this was a very simple calculation because it ends up being 1 times 10 to the negative 5th. But that's what my hydrogen concentration is going to be. And now, because I'm in units of concentration, I'm going to have a unit of molarity to describe it. Remember, capital M is describing it. So why don't you try the next 4? This is what you should end up with. Just do the best. So we want to match the sig figs to the best of our ability. So looking at the last one here, your number could be written in 2 ways. I prefer to see it in scientific notation, but as long as it's like 0.3, so if it's as long as it's within 100th, so that's fine to write it like you normally would. but beyond 100th, so that would be times 10 to the negative second. Beyond that point, you should write them all in scientific notation to help clarify what you have. So again, these all have a unit of molarity. pHs do not have a unit of molarity. So this is kind of explaining what we just did in words. So this first one, it's showing you the pH is equal to the negative log of the hydrogen concentration. So you do the exact same thing we did before. So you would do negative log of 0.0035, which would give you 2.5 as the pH. And remember, pH have no units. So the same idea applies to bases, except we're finding the pOH. So when you plug in the base concentration, you're doing the exact same thing. However, now instead of saying the pH, you're going to say the pOH is going to be 2.5. If you wanted the pH, you would then take 14 minus 2.5, and that would give you 11.5 as your pH. pH are the numbers you're kind of more used to working with. pOH is probably something you've never seen before. However, it is something that is still important to keep in mind. So like I said before, pH plus pOH is equal to 14. So if you were solving here, you would take 14 minus your pOH to get your pH, and vice versa. So let's look at another one. We have 0.0125 molarity of LiOH. So we're going to plug that into our calculator. Because this is a base, this is going to give us pOH. So our pOH would be negative log. So our pOH is going to be 1.90. So then our pH would be 14 minus 1.90. So it would be 12.1. So the 12.1 would be the pH. You want to kind of think of this from what you're used to. You're used to thinking that bases have a pH of 8 to 14. So if you have a base and you're getting a pH of 2, something's wrong. So you always want to kind of think of what you're working with when it's an obvious thing. So in the next one, we have a drink. We have a pH of 2.7. We want to know the hydrogen ion concentration. So we're going to do the exact same thing that we've been doing before. So we're going from pH to hydrogen concentration. So it's going to be the anti-log of the negative pH, which in this case is 10 to the negative 2.7. Or the anti-log, and I'm going to end up with 0.001995, but we would write that in scientific notation, and it would we would probably keep 2 sig figs, so we would put 2.0 times 10 to the negative third molarity. So either would be an acceptable answer for us. There's some more practice here. The first one, so we're following the same process that we did for the hydrogen. It's just the negative log of the hydroxide ion, and it gives us these pOH values. So the next one is kind of a more common thing that you would see. So usually when you're given the hydroxide concentration, they'll ask you for the pH because that's a number you're more familiar with. So in the next set of problems, you kind of have 2 steps. The first step is going to be calculating your pOH, which you do the exact same thing. So the negative log of 5.0 e to the negative 9 will give me 8.3 as my pOH. So then I'm going to take 14 minus 8.3, and that will give me my pH, which is 5.7. So this one's kind of a 2-step problem. It's very important that you take a look at what you're given. So in this case, you're given the hydroxide concentration and what you're finding. So if I had a hydroxide concentration, which is a base, and I said that it had this concentration, which gave me 8.3, It wouldn't make a lot of sense because it's a very low concentration, so it makes more sense for a pH of 5.7. So try the remaining 3. So these are the values you should end up with for your pOH and your pH. Usually when you're thinking about pH values, they're more familiar to you when you're thinking of it. Is it acidic, basic, or neutral? So all aqueous solutions contain both the hydrogen ion and the hydroxide ion because water itself is going to break apart into that. So water all on its own does this. So in a basic solution there may not be a lot of H, but as long as there's any water in your solution, you're going to find some hydrogen ions. Similarly, acidic solutions also contain small amounts of hydroxide ions because whenever water is present, there must also be the hydroxide. So this little chart right here is something that's very helpful to students, especially if you do your pH practice homework, which includes a chart. Because you do need to kind of go all the way from, one end to the other. This equation right in the middle, I tend not to use. You're welcome to use it if you like. Just be careful because technically your units here are molarity squared because you're multiplying 2 molarities together. The one on the top is my preferred way, the 14 method. Your answers, it's not going to change your answers if you're using it properly though. This is something that would not be given to you on a test. It would be something you would have to know.